So far in the last videos, we have assumed that our diode is an ideal diode, and for an ideal diode in the on mode, the diodes acts like a short circuit, and in off mode, the diode acts like an open circuit. This is the model of an ideal diode. But as we know in real life, there is nothing ideal. So we will discuss some non-idealities that real diodes have. So if you remember from the last lecture, this diode, since this voltage is positive and this voltage is zero, the current will try to flow in this direction, and the diode will allow all such currents. So since it is an ideal diode, we will replace it using a short circuit. .5 volt. Since this is a short circuit, the voltage will be zero, and the current will be the current through the resistance, which is 5 volt divided by 2.5 kilo ohm, which is 2 milliampere. Now, what about the power consumed by the diode? If you remember from CSE250, the formula for calculating the power consumed by a device is equal to voltage times the current. Here the voltage is 0 volt and the current is 2 milliampere. So the power will be 0 times 2, which is 0. Now this is odd because a diode is a passive device and there are current flowing through this device, but still we see that the device is not consuming any power. In real life, this is not possible. So the assumption that our assumption that the voltage is zero is slightly wrong. Another thing that we assumed is that there are no voltage drops here. This means that the material that the diode is made of has zero resistance. So this is also not possible in real life, because in real life even a pure conductive wire, for example copper or gold, they have some resistance, right? Some small, very small resistance. So we have to take these two factors into account. Let's see how we can do that. First, let's consider the power case, the non-ideality of power. So for example, if you take a diode and the voltage is VD and the current through is ID. Say you measured the voltage using a voltmeter and you measured the current using an ammeter. Now, if you perform this experiment, what you will find is that the power consumed by this device is directly proportional to the diode current. The power is directly proportional to the diode current. If we increase the current by two times, the power will also increase by 2 times. This is not like resistance, because the power consumed by resistance is I squared R. So in this case, the power is proportional to the square of the current. But for a diode, it is proportional directly to the current. Well, do we know any device for which the power is directly proportional to the current? If you consider a voltage source with voltage VD, and if you assume that it's consuming power, so the current is flowing in this direction, then since voltage is constant, we can write P is equal to VD times I. Now, since the voltage is constant, we can write the power is proportional to the current. So what we have learned is that uh, when the diode is conducting, when it is in on mode, the power is proportional to the current, which is similar to that of a voltage source. And if we perform the experiment, and we can, since this is proportional, we can write some proportional constant K times ID. If we perform the experiment for silicon diodes, that means the diodes that are made of silicon, we see that the value is around 0.7. So if we match this equation with that of a voltage source, we can say that when the diode is in on mode, we can replace it using a voltage source with a value of voltage Vd, which is approximately 0.7 volt only for silicon diodes. Note that the positive side of the voltage source will be connected to the anode of the diode, and the negative side will be connected to the cathode. So when the diode is in on mode, we can replace it using a voltage source. What about in off mode? Well, in off mode, we will still replace it using an open circuit, because in off mode there are no current flowing, so the power is still zero because the current is zero. So we did not need to modify the off condition. We only need to modify the on condition. Now, if we apply a voltage, say there is a resistance. So if we apply a voltage, say 10 volt, then what this means that when the Vd will be 0.7, it means that the diode will consume 0.7 volt of voltage. So the voltage output, or the voltage across the resistance, will be 10 minus 0.7, which is 9.3 volt if the diode is on. So we can take the power into factor by replacing it with a voltage source instead of a short circuit in the on mode. Now what about the material? Because the diode is made of a real material, and every material, even if it is a conductor, has some resistance. So instead of a short circuit, we can model this as a voltage source in series with a resistance Vd. This is the positive side would be connected to anode, and the negative side would be connected to cathode. So the value of this resistance is very small. It's around 10 ohm or 12 ohm, or in some cases it can be 9 ohm or even lower values. This is a very small resistance compared to the resistances that we connect in a diode circuit. For example, in this case, the resistance is 2.5 kilo ohm or 2500 ohm. So 10 ohm compared to this 2500 is very small. So in most of the cases, we can ignore this resistance. But for a more accurate model, we should include this resistance. So these are the two non-idealities that a real diode has.